gravitational interaction could be sculpting the expanding gas, directing it along preferred axes. This would explain the sharp edges seen in the nebula and the apparent lack of chaotic turbulence that typically characterizes similar objects. The central star is likely in an advanced evolutionary stage, either approaching a transition to a Wolf-Rayet phase or nearing its final collapse. The material ejected into space could be part of a larger process in which layers of stellar atmosphere are shed over time, forming structured nebulae that persist long after the original outburst. The exact mechanism behind the symmetry remains a topic of ongoing study, with hypotheses ranging from episodic eruptions caused by internal instability to a controlled expansion influenced by a strong toroidal magnetic field. Spectroscopic analysis reveals that the nebula is rich in both silicate and carbon-based dust, suggesting complex chemical interactions occurring within its expanding shell. The presence of ionized hydrogen and oxygen lines indicates exposure to intense ultraviolet radiation, which is slowly altering the composition of the surrounding medium. These processes are crucial in enriching the interstellar environment with heavy elements that later contribute to the formation of new generations of stars and planetary systems. The velocity of the expanding gas suggests that the nebula has been evolving for thousands of years, though it is unclear whether it has remained stable over time or if it has undergone significant changes in structure. Some researchers propose that the formation is an optical illusion, where a more cylindrical or bipolar outflow appears squared due to our viewing angle. Others argue that external influences, such as a dense interstellar medium or remnant stellar winds, may be reinforcing the shape by constraining material along specific planes. Advanced telescopes equipped with high-resolution spectrographs are expected to provide more precise data on the velocity distribution of gas and dust. By analyzing how light interacts with different regions, astronomers hope to reconstruct the three-dimensional shape and determine whether the observed symmetry is an inherent property or a temporary phase. If the central star is approaching a supernova event, its surrounding nebula could dramatically brighten as the explosion interacts with the ejected material, similar to what has been observed in other massive star systems. Comparisons to other structured nebulae suggest that mass loss in massive stars follows patterns that are more organized than previously thought. While planetary nebulae often display symmetric forms due to the expansion of shells around dying stars, this particular object exhibits a level of precision that challenges conventional models. If magnetic forces are indeed playing a dominant role, it may suggest that similar structures could exist elsewhere but remain undetected due to their orientation or distance from Earth. Infrared observations have also hinted at the presence of complex organic molecules within the nebula, which could have formed through photochemical reactions triggered by high-energy radiation. Such environments are thought to be crucial in the early stages of planetary system development, as they contribute to the formation of prebiotic compounds that later become part of interstellar dust clouds. Understanding how these materials evolve in different stellar environments provides insight into the chemical diversity of the galaxy. Future research will focus on mapping the precise movement of gas within the nebula and determining whether external factors are influencing its evolution. If a binary companion is confirmed, it could provide further evidence that multiple star systems are a key factor in shaping structured nebulae. Long-term monitoring may reveal subtle shifts in brightness or morphology, indicating ongoing dynamic processes that have yet to be fully understood. If the central star eventually undergoes a supernova, it could transform the surrounding region by sending shockwaves through the nebula, triggering secondary reactions and possibly altering its structure. The resulting supernova remnant would provide valuable data on how pre-existing mass loss affects the aftermath of stellar explosions. If a neutron star or black hole forms at the core, it may interact with the surrounding material in ways that produce additional high-energy emissions, making it a potential source of radio waves or X-ray bursts. The precision of the formation continues to challenge existing astrophysical models, suggesting that either previously unknown mechanisms are at work or that magnetic shaping plays a far greater role in stellar evolution than currently assumed. Upcoming telescopes with adaptive optics and interferometry will provide deeper insights into the processes governing the expansion of ionized gas and the interaction between radiation and dust within the nebula. While its ultimate fate remains uncertain, its significance as an astrophysical case study is undeniable. Whether it is a short-lived phase of stellar evolution or a long-standing feature that will persist for thousands of years, it represents a rare and valuable opportunity to study the forces that shape the most massive stars in the cosmos. The answers it holds could refine our understanding of how stars evolve, how they lose mass, and how they influence the galactic environment over cosmic timescales. The forces responsible for shaping this nebula remain a subject of debate, with multiple mechanisms potentially working in tandem to maintain its strikingly structured form. The presence of a dense circumstellar medium suggests that earlier mass ejection events may have interacted with surrounding material, creating shock fronts that reinforced the observed geometry. If stellar winds or episodic eruptions from the central star were directed by an unseen companion, their effects could have compounded over time, gradually sculpting the nebula into its current configuration. Magnetic fields are another possible factor influencing its development. In some high-energy astrophysical environments, magnetic pressure can guide ionized gas along preferred paths, constraining outflows into collimated jets or symmetric lobes. If this phenomenon is occurring here, it could help explain the sharp definition of the nebula's edges and the near-identical structure on opposite sides of the central star. Observations of other massive stellar remnants have shown that even weak magnetic fields can have a profound impact on outflow dynamics, reinforcing the idea that this nebula's shape may be magnetically driven. The chemical complexity of the surrounding gas adds another layer of intrigue. The discovery of molecular hydrogen and polycyclic aromatic hydrocarbons within the nebula suggests that the region has undergone prolonged exposure to ultraviolet radiation, leading to chemical reactions that produce complex organic compounds. If this material later becomes part of interstellar clouds, it could contribute to the formation of planets or even prebiotic chemistry in future stellar systems. This highlights the role of evolved stars not only as sources of heavy elements but also as potential contributors to the early chemistry of planetary environments. The velocity distribution of ejected material is also a critical factor in understanding the formation of the nebula. If the gas is expanding uniformly, it would suggest that the star has been losing mass gradually over an extended period. However, if velocity gradients are detected, with some regions moving faster than others, it could indicate episodic bursts of energy, possibly linked to a hidden binary companion or internal stellar instability. High-resolution spectroscopic studies will help determine whether the structure has remained stable or if it is actively evolving, with changes in brightness or morphology providing additional clues. Comparisons to other known stellar outflows provide valuable context for interpreting this structure. The similarity to bipolar planetary nebulae, which are often shaped by binary interactions, suggests that the nebula may represent an earlier stage of this process in a much more massive system. If future observations confirm the presence of an orbiting companion, it could provide strong evidence that binarity is a key factor in the formation of highly structured nebulae, challenging existing models of single-star mass loss. The possibility that the central star is approaching a terminal supernova phase adds an additional layer of urgency to ongoing research. If this is a pre-supernova system, then the surrounding nebula may play a crucial role in determining the characteristics of the eventual explosion. A dense circumstellar medium could shape the supernova's light curve, producing an extended afterglow or even influencing the type of remnant that forms. If the core collapse results in a neutron star or a black hole, the interaction between the compact object and the surrounding nebula could generate secondary emissions, including high-energy X-ray or radio bursts. Some researchers propose that this nebula represents a previously unrecognized category of structured stellar outflows, distinct from both planetary nebulae and classical supernova remnants. If so, it could mean that highly organized mass loss occurs in more stars than currently expected but remains undetected in systems with less favorable viewing angles. Advanced three-dimensional modeling, combined with data from next-generation telescopes, will be necessary to determine whether similar formations exist elsewhere in the galaxy. Long-term monitoring will be essential to track any changes in the nebula's structure. If subtle shifts in brightness or gas distribution are detected, it could indicate ongoing mass loss or dynamic interactions within the expanding material. Alternatively, if the nebula remains unchanged over decades of observation, it would suggest that its formation was driven by a past event rather than active processes occurring in the present. Either scenario will provide valuable insights into how massive stars shed their outer layers and how those layers evolve over time. The nebula's role in the broader astrophysical landscape extends beyond its immediate surroundings. If it is indeed an example of a structured pre-supernova outflow, it could help refine predictions for other massive stars nearing the end of their life cycles. Understanding the processes shaping this formation could improve models of how supernovae interact with their environments, potentially leading to better interpretations of historical supernova remnants observed throughout the galaxy. Future research will focus on uncovering the underlying drivers of the nebula's symmetry, whether they be magnetic forces, binary interactions, or unknown stellar dynamics. Upcoming missions and observational campaigns will provide increasingly detailed data, helping to answer fundamental questions about the role of evolved stars in shaping the structure of the interstellar medium. Regardless of what mechanisms are ultimately responsible, the nebula remains a rare and invaluable opportunity to study the complex interplay between stellar evolution, mass loss, and the physical forces that govern the cosmos. As observational techniques continue to improve, new details about this enigmatic formation will likely emerge, shedding light on the precise mechanisms responsible for its near-perfect symmetry. The role of radiation pressure in shaping the expanding gas is an area of active investigation, as intense stellar winds could be driving material outward along well-defined paths. If the star is emitting energy anisotropically, with stronger radiation in specific directions, it could be influencing the way ejected material disperses into space. This could help explain the structured nature of the nebula, particularly if interactions with a surrounding dust disk or magnetic field are reinforcing its geometric appearance. High-energy phenomena may also be contributing to the evolution of this structure. Some researchers suggest that the presence of shock fronts, regions where fast-moving gas collides with slower material, could be shaping the expanding nebula. These interactions create areas of increased density and ionization, altering how light scatters and giving the nebula its distinctive brightness distribution. If these shocks are being driven by periodic stellar outbursts, then the formation could be the result of multiple ejection events over time, each adding to the overall complexity of its structure. Infrared observations continue to provide new insights into the dust and gas composition of the surrounding environment. Data suggests that the dust grains within the nebula are relatively large compared to those found in diffuse interstellar clouds, possibly indicating that they have undergone significant processing due to radiation collisions. If this region is rich in carbon-based compounds, it could support the idea that evolved stars contribute not only to heavy element enrichment but also to the formation of molecular precursors essential for planetary system development. Determining the precise age of the nebula is another critical aspect of ongoing research. By analyzing the expansion velocity of different gas layers, astronomers aim to estimate when the initial mass ejection occurred. If the nebula is relatively young, it could be the result of a recent instability in the central star, whereas an older formation would suggest a more gradual mass loss process over an extended period. This distinction is important in understanding whether this structure is a transient phase that will evolve into a more diffuse remnant or if it represents a long-lived phenomenon sustained by continuous energy input. The potential presence of a binary companion remains a crucial question, as its confirmation would provide a strong explanation for the nebula's ordered structure. If a secondary star is orbiting the central object, its gravitational influence could be directing material into specific flow patterns, producing the observed symmetry. Some models suggest that if a white dwarf, neutron star, or even a black hole is present, accretion-driven outflows could be responsible for the formation's striking shape. Identifying subtle variations in the motion of the primary star or detecting indirect signs of a hidden companion through X-ray or radio emissions may help resolve this mystery. Further study of the polarization of light from the nebula will be useful in determining whether magnetic forces are playing a significant role in its evolution. If light scattering patterns indicate the presence of aligned dust grains, it could suggest that a strong magnetic field is guiding the expansion of gas. Such a scenario would align with models of magnetically collimated outflows, which have been observed in other astrophysical environments, including young stellar objects and active galactic nuclei. One of the most intriguing possibilities is that this formation represents an early stage of a process that has not been widely documented in astrophysics. If it turns out to be a precursor to a more well-known structure, such as a planetary nebula or a supernova remnant, it could provide a unique opportunity to study how these phenomena develop over time. Observing how the nebula changes in the coming years will be crucial in determining its future trajectory, whether it will eventually dissipate into the interstellar medium or continue evolving into a more complex structure. If the central star ultimately undergoes a supernova, the surrounding material could play a key role in shaping the explosion's observable characteristics. The presence of dense circumstellar matter could cause significant interaction between the supernova shockwave and the pre-existing nebula, leading to an unusually bright and prolonged event. If this occurs, it could offer direct observational evidence of how mass loss influences the final stages of massive star evolution. Long-term monitoring with next-generation telescopes will be essential in answering the remaining questions surrounding this extraordinary structure. Instruments capable of resolving fine details in the gas distribution, magnetic field orientation, and spectral properties will provide the data needed to construct a more complete picture of its origins and evolution. If similar objects are identified elsewhere in the galaxy, it may indicate that these types of structured outflows are more common than currently believed, potentially leading to a re-evaluation of existing models of stellar mass loss. Regardless of its ultimate fate, this nebula remains one of the most visually striking and scientifically valuable examples of how complex forces interact in the late stages of stellar evolution. Whether shaped by binary dynamics, magnetic fields, episodic outbursts, or a combination of multiple factors, its existence challenges conventional astrophysical theories and offers an unparalleled opportunity to study the intricate processes governing massive stars. Future observations will undoubtedly bring new discoveries, deepening our understanding of how these cosmic structures form, persist, and eventually transform into the next generation of celestial phenomena. As observations continue to refine our understanding of this extraordinary formation, the interplay between multiple astrophysical forces becomes increasingly apparent. The near-perfect symmetry suggests that a finely tuned combination of stellar winds, radiation pressure, gravitational dynamics, and possibly magnetic confinement is at work. Each of these factors contributes to shaping the expanding shell of gas and dust, maintaining its structural integrity over time. Whether this level of organization is an inherent property of certain types of stellar outflows or a rare coincidence of conditions remains an open question. Infrared spectroscopy has revealed variations in the temperature and density of different regions within the nebula, indicating that it is not a uniform shell but rather a complex, layered structure. This suggests that multiple ejection events may have occurred at different times, each adding a new component to the overall formation. If past eruptions have been episodic, possibly regulated by internal instabilities in the central star or interactions with an orbiting companion, the nebula could be an evolving record of its progenitor's mass loss history. The detection of specific ionized elements in the surrounding gas suggests that high-energy radiation from the central star is actively altering its chemical composition. Regions exposed to the most intense ultraviolet and X-ray flux exhibit signs of ionization-driven molecular dissociation, while more shielded areas retain heavier molecules and dust grains. This dynamic environment provides insights into how massive stars influence their surroundings, gradually enriching the interstellar medium with elements forged in their interiors. One of the primary challenges in understanding the nature of this structure is determining whether its symmetry is a transient feature or a long-term characteristic. If it is the result of a recent outburst, it may slowly degrade over time as the expanding material interacts with external forces. On the other hand, if it is stabilized by ongoing processes, such as a sustained mass flow or a persistent magnetic field, its geometry may remain largely unchanged for thousands of years. Tracking subtle shifts in the nebula's brightness and morphology over successive observational periods will be essential in distinguishing between these possibilities. Comparisons to other known examples of structured nebulae suggest that ordered mass ejections are more common than previously assumed. However, the degree of symmetry observed here is exceptionally rare, indicating that specific conditions must be met for such formations to arise. If future surveys identify similar objects in different regions of the galaxy, it could provide a broader statistical foundation for understanding how often these structures occur and what factors contribute to their development. Advanced numerical simulations are being used to model the potential formation scenarios for this system. By incorporating variables such as stellar rotation, pulsation-driven mass loss, and binary interactions, researchers hope to replicate the observed structure and determine which forces dominate its evolution. Early results suggest that a combination of rapid stellar rotation and a companion's gravitational influence could create flow patterns that resemble the nebula's distinct shape. If these models prove accurate, they could offer a new perspective on the role of binarity in shaping circumstellar environments. Another intriguing aspect is the potential for future variability in the central star itself. If it is nearing the end of its evolutionary cycle, further instability may lead to additional mass ejections or luminosity fluctuations. Such changes could provide direct observational evidence of how the formation is being influenced by ongoing stellar processes. If a sudden brightening event occurs, it could be a sign of an impending transformation, possibly signaling the transition into a Wolf-Rayet phase or even the approach of a terminal explosion. If the star ultimately undergoes a core collapse supernova, the surrounding nebula could play a critical role in shaping the aftermath. A dense pre-existing medium could result in an unusually energetic explosion, with shockwaves producing intricate interaction patterns within the already structured outflows. Such an event would be a rare opportunity to observe how massive stars influence their own supernova environments, offering insights into the processes that govern the final stages of stellar life. Long-term monitoring efforts will focus on detecting changes in expansion velocity, ionization levels, and thermal emissions within the nebula. Any deviations from the expected behavior could indicate previously unknown influences at work, potentially revealing new physics governing stellar outflows. With upcoming space-based and ground-based observatories providing increasingly detailed data, a clearer picture of this remarkable formation will continue to emerge. Whether this structure is an exceptional case or part of a broader, yet underappreciated category of organized mass ejections, its study is reshaping perspectives on how stars interact with their surroundings. The precise forces maintaining its near-perfect symmetry remain one of the most compelling mysteries in modern astrophysics, and future discoveries may provide the missing pieces needed to unlock its true nature. Regardless of what new revelations come to light, this nebula stands as a striking testament to the complex and often unexpected beauty of stellar evolution. The persistence of such a structured formation raises fundamental questions about the longevity of ordered nebulae and the mechanisms that sustain their geometry over time. If the observed symmetry is not merely a transient effect, then ongoing processes must be actively maintaining its precise form. One possibility is that the radiation pressure from the central star is continually shaping the expanding gas, reinforcing existing structures and preventing dissipation. In this case, variations in stellar output could lead to subtle but measurable shifts in the nebula's morphology, offering insights into how radiation-driven mass loss influences circumstellar environments. The presence of complex molecular compounds within the expanding shell suggests that chemical evolution is occurring on a large scale. As ultraviolet and X-ray radiation interacts with dust and gas, it triggers photodissociation processes that break apart existing molecules and encourage the formation of new ones. This cycle of destruction and recombination is key to understanding how massive stars contribute to the molecular diversity of interstellar space. If the conditions within the nebula are stable enough, they may support the gradual synthesis of increasingly complex compounds, further enriching the surrounding medium. Velocity mapping of the nebula's outflows is another avenue of investigation that may yield crucial insights into its formation history. If different layers of gas are expanding at distinct rates, it could suggest multiple episodes of mass ejection, each contributing to the overall structure. By reconstructing the motion of individual gas clouds within the nebula, astronomers can determine whether the expansion is accelerating, slowing down, or maintaining a steady rate. A uniform velocity distribution would support the idea of a single, well-coordinated outflow event, while irregularities could indicate ongoing dynamic interactions between different layers of material. The role of external influences, such as interactions with the surrounding interstellar medium, is also worth exploring. If the expanding nebula is encountering regions of higher density gas, it could be experiencing external pressure that helps define its shape. This scenario is particularly intriguing because it would imply that the large-scale structure of the interstellar medium plays an active role in shaping stellar remnants. If such interactions are confirmed, they could offer a broader context for understanding how similar nebulae form across different galactic environments. Advances in computational astrophysics are enabling the development of increasingly sophisticated simulations that attempt to recreate the conditions necessary for such a structured formation. These models incorporate factors such as stellar rotation, magnetic field dynamics, radiation transport, and binary gravitational effects. The goal is to determine whether a single dominant force is responsible for shaping the nebula or if multiple factors are working together in a complex interplay. Early results suggest that while radiation pressure and magnetic fields alone can produce organized outflows, the addition of a binary companion significantly enhances the likelihood of maintaining long-term symmetry. If a compact object is present within the system, it could further complicate the dynamics of the nebula. A neutron star or black hole companion could be influencing the surrounding material through accretion-driven winds or relativistic jets. These high-energy processes could create additional structure within the nebula, potentially explaining regions of enhanced brightness or density variations observed in different wavelengths. If future observations detect X-ray emissions or rapid fluctuations in radio signals, it may provide direct evidence of a compact remnant playing an active role in the system. Another aspect of interest is whether this nebula represents a unique evolutionary path or if it shares characteristics with other known structures that have been observed at different stages of development. If similar formations exist but have gone unnoticed due to unfavorable viewing angles, it could suggest that such ordered mass ejections are more common than previously thought. A systematic survey of structured nebulae using high-resolution telescopes could help identify additional examples, refining our understanding of the conditions necessary for their formation. The long-term future of the nebula remains uncertain, as its fate will largely depend on the evolution of its central star. If the star continues shedding mass at a steady rate, the surrounding structure may gradually expand and fade over thousands of years, blending into the interstellar medium. Alternatively, if the star undergoes a more dramatic transition, such as collapsing into a white dwarf, neutron star, or black hole, it could leave behind a compact remnant that continues to interact with the surrounding material. If this leads to periodic bursts of energy, the nebula may experience episodic reillumination, creating a variable emission profile that persists long after the initial mass ejection event. If a supernova does occur within the nebula, it could produce one of the most visually and scientifically interesting supernova shockwave propagates, creating intricate patterns of glowing filaments and ionized gas. The resulting explosion could provide valuable data on how mass loss before core collapse affects the properties of the supernova itself, offering a real-world test case for theoretical models of stellar death. Regardless of its ultimate fate, this nebula remains an astrophysical anomaly that continues to challenge conventional understanding. Its striking symmetry, dynamic environment, and potential connection to high-energy astrophysical processes make it an ideal subject for continued study. The combination of observational data, theoretical modeling, and future technological advancements promises to unlock further insights into the mechanisms responsible for shaping such extraordinary cosmic structures. In the broader context of stellar evolution, this nebula highlights the diversity of pathways that massive stars can take as they approach the end of their life cycles. Whether it represents a transient phenomenon or a more persistent stage of mass loss, it serves as a reminder that the processes governing the formation and evolution of stellar remnants are more intricate than previously assumed. As research continues, each new discovery will bring us closer to understanding the fundamental forces that sculpt the universe's most fascinating and mysterious celestial objects. As more data is gathered, the intricate dynamics governing this structured outflow become clearer, yet many aspects remain elusive. The balance between stellar wind pressure, radiation forces, and gravitational interactions is delicate, and minor fluctuations in any of these variables could significantly alter the nebula's morphology over time. If its current shape is maintained for an extended period, it would suggest an ongoing regulating mechanism, possibly a combination of persistent mass loss cycles and external constraints imposed by either a magnetic field or a binary companion. A deeper understanding of the internal motion of the gas is crucial in deciphering whether the structure is static or evolving. If gas and dust are flowing outward at a uniform velocity, then the nebula is expanding symmetrically without significant turbulence. However, if regions within the outflow exhibit differences in acceleration, it may indicate that multiple processes are acting simultaneously. The presence of high-velocity streams, for example, could point to localized shock waves where ejected material interacts with remnants of previous stellar mass loss. If the star at the center is rotating rapidly, it could also be affecting the mass ejection pattern. Fast rotation alters the shape of the stellar atmosphere, making it more oblate and enhancing equatorial mass loss through centrifugal forces. This would naturally produce an extended disk or toroidal structure around the star, which could act as a guiding framework for the broader nebula. If rotation is a key factor, then future spectroscopic studies of the star's surface may reveal Doppler broadening effects, indicating differential velocity regions across its surface. The role of ionization fronts within the nebula is another aspect of interest. If the central star's radiation is continuously exciting the surrounding gas, it may be forming stratified layers where different elements are ionized at varying depths. This would lead to a multi-tiered composition where hydrogen, helium, oxygen, and heavier elements are distributed according to their ionization potentials. Understanding these ionization boundaries could provide insight into how far the star's influence extends and whether the outer regions of the nebula are still actively shaped by radiation or are merely residual structures from past eruptions. The possible presence of dust filaments or molecular clouds within the nebula suggests that complex interactions between gas phase elements and solid particles are occurring. Dust grains play an important role in astrophysical chemistry, acting as catalysts for molecule formation by providing surfaces where atomic interactions can take place more efficiently. It is rich in carbonaceous or silicate dust. It may indicate that material from the star is condensing into solid form, eventually contributing to the raw material for future planetary system formation. One key observational goal is to determine whether the nebula is optically thick or if it allows significant amounts of radiation to escape. If it is largely transparent at certain wavelengths, then light from the central star may be escaping in directed beams, influencing surrounding interstellar clouds beyond the immediate boundaries of the structure. This could result in faint emission regions detectable in infrared or radio wavelengths, providing clues about how the nebula interacts with the broader galactic environment. The possibility of a faint, extended halo surrounding the main structure is also being explored. Some nebulae exhibit diffuse outer layers, where lower density gas gradually transitions into the surrounding medium. Follows a extended out is not immediate in current observations but could be revealed through deep exposure imaging techniques. If such a halo is present, it may contain older material from earlier mass ejections, offering a more complete picture of the star's long-term evolution. Further study of light polarization within the nebula may also help in determining whether magnetic fields are contributing to its structure. If dust grains are aligned along a preferred axis, it could indicate that an underlying magnetic field is shaping the flow of ionized gas. Strong magnetic confinement could explain why material appears to be expanding in a highly organized manner rather than dissipating irregularly, as is typical in many other stellar outflows. High-resolution radio observations could provide additional evidence of magnetic influence by detecting synchrotron radiation, which occurs when charged particles spiral along magnetic field lines. The long-term monitoring of the nebula's brightness and shape will provide important clues about its future evolution. If no significant changes are observed over the coming decades, it could suggest that the system has reached a stable equilibrium, where forces acting within it counterbalance one another. However, if gradual shifts in emission intensity or structural features are detected, it may indicate that the nebula is still undergoing active reshaping, driven either by continued mass loss or external forces acting on the expanding shell. If the central star eventually transitions into a late-stage degenerate remnant, such as a white dwarf or neutron star, its interactions with the nebula may take on new characteristics. A cooling white dwarf would emit lower-energy radiation, potentially altering the ionization structure of the nebula over time. If a neutron star or black hole forms, accretion of remaining material could generate episodic bursts of high-energy emissions, further complicating the evolutionary trajectory of the surrounding gas. With the advent of more sensitive astronomical instruments, including future space-based and ground-based telescopes, finer details of the nebula's composition and kinematics will become accessible. Multi-wavelength campaigns combining optical, infrared, radio, and X-ray data will allow researchers to construct an increasingly refined model of the processes governing this remarkable structure. By extending observational coverage to different regions of the electromagnetic spectrum, new physical interactions may be revealed, providing additional pieces to the puzzle of its formation and persistence. Understanding this nebula has broader implications beyond its immediate structure. If similar objects are discovered in different star-forming regions or near other evolved stellar systems, it could indicate that such formations represent a recurring phase in the life cycles of massive stars. This would provide new constraints on theories of stellar mass loss and the role of binarity, magnetic fields, and radiation pressure in shaping astrophysical outflows. Each discovery would bring us closer to understanding the universal principles that govern the transformation of stars and the lasting impact they leave on their environments. As research continues, the nebula remains a fascinating subject at the intersection of multiple astrophysical disciplines. Its structured appearance challenges traditional models, suggesting that either previously unrecognized mechanisms are at work or that known processes are operating in a more complex manner than currently understood. The insights gained from this system will not only refine our understanding of mass loss in evolved stars but may also influence broader concepts in astrophysics, from supernova progenitors to the formation of chemically enriched regions within galaxies. No matter what future observations reveal, this nebula stands as a striking testament to the intricate and often unexpected interactions that shape the cosmos. The persistence of such an intricate and symmetrical structure suggests that it is not merely a fleeting phase but a system governed by sustained forces. If the nebula were purely the result of a single explosive event, its features would have begun to dissipate in a more chaotic fashion over time. Instead, the defined edges and organized outflows indicate that ongoing mechanisms are reinforcing its structure, preventing it from dissolving into an irregular cloud. Understanding the nature of these stabilizing forces will provide crucial insights into how long such formations can persist and what role they play in the broader galactic ecosystem. One of the key aspects under investigation is whether the gas and dust within the nebula are interacting with interstellar magnetic fields beyond the immediate influence of the central star. If so, the entire system may be embedded within a larger-scale magnetized region that is influencing the way material is distributed. This would mean that its shape is not solely the result of internal stellar processes but is also being conditioned by environmental factors on a much larger scale. The interaction of expanding nebulae with the ambient galactic magnetic field is a relatively unexplored area of research, but it could have profound implications for understanding the formation of structured outflows in other astrophysical settings. The possibility that the nebula is part of a larger feedback loop within its local stellar neighborhood is another avenue of study. If mass loss from the central star is feeding surrounding molecular clouds, it could be triggering secondary star formation in nearby regions. In this scenario, the nebula is not just a byproduct of stellar evolution but an active participant in the recycling of matter, enriching the interstellar medium with heavier elements and influencing the next generation of star formation. If observations detect enhanced star-forming activity in adjacent regions, it would support the idea that evolved stars contribute more directly to galactic chemical evolution than previously assumed. Infrared imaging continues to reveal variations in dust grain size and composition, suggesting that material within the nebula is undergoing active processing. Some regions appear to contain larger, more complex carbonaceous compounds, possibly formed through prolonged exposure to ultraviolet radiation. If dust grains within the nebula have been altered by repeated ionization cycles, they may exhibit unique spectral signatures that could serve as a marker for similar objects elsewhere in the galaxy. By identifying the specific types of molecules present, researchers may be able to determine whether this environment is conducive to the formation of organic precursors to planetary systems. The thermal structure of the nebula is another critical factor in assessing its long-term stability. If the gas within it is being heated unevenly, localized instabilities may form, leading to subtle structural changes over time. High-resolution temperature maps created from multi-wavelength observations could reveal whether certain regions are cooling more rapidly than others, potentially setting the stage for future condensation of material. If dense clumps are forming within the nebula, they could eventually collapse under their own gravity, leading to the formation of new stellar objects. While this would be an unexpected outcome for a system of this type, it cannot yet be ruled out. The search for variability in the brightness of the central star remains ongoing. If the star exhibits periodic fluctuations in luminosity, it may indicate pulsational instabilities affecting its outer layers. These variations could, in turn, influence the mass loss rate, leading to episodic enhancements in the nebula's structure. If brightness changes are detected, correlating them with observed changes in the nebula's emission patterns could help establish a direct link between stellar activity and the evolution of the surrounding material. The outermost layers of the nebula are of particular interest, as they may provide a record of its earliest formation stages. If weak shock waves are detected propagating through the outer edges, it could suggest that the nebula is still expanding into previously undisturbed interstellar space. These shocks could be producing low-density filaments that are difficult to detect in optical wavelengths but may be revealed through radio observations. If such features are confirmed, they would provide valuable clues about the nebula's expansion dynamics and whether it is still actively interacting with its environment. One of the most significant remaining uncertainties is whether this structure represents a phase that other massive stars undergo or if it is an exceptional case. If similar objects exist but have not yet been identified, it could mean that such nebulae are more common than previously thought but remain undetected due to observational limitations. Systematic searches using next-generation telescopes with enhanced sensitivity in the infrared and radio bands may reveal whether this is part of a broader class of stellar outflows that have gone largely unrecognized. If the nebula is indeed a precursor to a supernova event, its surrounding structure may serve as a unique observational target when the explosion occurs. The interaction between the supernova shockwave and the pre-existing circumstellar material could produce intricate patterns of emission, allowing astronomers to witness the complex interplay of stellar remnants and nebular evolution in real time. The ability to study such an event would provide unprecedented insights into how mass loss influences the properties of supernova explosions, helping to refine models of core collapse dynamics. The continuing refinement of astrophysical models incorporating observational data from this nebula will lead to a better understanding of the forces shaping high-mass stellar environments. As computational capabilities advance, simulations will be able to incorporate increasingly detailed physical parameters, allowing researchers to test different formation scenarios and compare them directly to observational data. If a definitive explanation for the nebula's structure emerges, it will not only resolve one of the most intriguing astrophysical mysteries but also provide a framework for understanding similar objects that may be discovered in the future. Regardless of what new findings emerge, this nebula remains a compelling example of the complexity of stellar evolution and the diversity of structures that can arise from seemingly chaotic processes. Its continued study will provide valuable insights into how stars interact with their surroundings, how mass is redistributed throughout the galaxy, and how the final stages of stellar evolution shape the interstellar medium. Each new observation brings us closer to uncovering the full story behind this remarkable formation, revealing the intricate and often unexpected ways in which stars leave their mark on the cosmos. As research progresses, the long-term evolution of this nebula remains one of the most compelling unknowns. Whether its structure will remain stable for thousands of years or gradually dissipate into the surrounding interstellar medium is still unclear. If the forces maintaining its symmetry weaken over time, the well-defined edges may begin to blur as expanding gas disperses. However, if there are persistent shaping mechanisms, such as ongoing stellar mass loss, magnetic field interactions, or external pressure from surrounding interstellar clouds, the structure may remain largely intact for an extended period. Observations in multiple wavelengths continue to refine our understanding of the nebula's internal structure. Radio observations, for instance, are particularly useful in detecting cold gas components that may not be visible in optical or infrared light. If significant amounts of molecular gas are present, it could indicate that the outer layers of the nebula are cooling and condensing, which might lead to the formation of secondary features such as filamentary streams or localized high-density regions. These structures, if confirmed, would provide further evidence of ongoing interactions between stellar ejecta and the surrounding environment. The distribution of heavier elements within the nebula is also of interest. If enriched materials such as oxygen, nitrogen, and carbon are concentrated in specific regions, it could suggest that different layers of gas are expanding at different rates or that localized ionization fronts are influencing chemical processes. Detailed spectral analysis may reveal whether these elements were produced in earlier nuclear fusion cycles within the central star or if they are the result of more recent nucleosynthesis in an unstable stellar atmosphere. Another crucial factor in understanding the nebula's evolution is determining whether it is interacting with external gas flows from other nearby stellar sources. If the region around the nebula contains additional massive stars that are shedding material, their outflows could be influencing the expansion and shape of the structure. This would suggest that nebular symmetry is not solely dictated by the properties of the central star but is also affected by its galactic environment. If such interactions are detected, they could provide new insights into how massive stars shape their surroundings on a larger scale. The question of whether the central star is truly alone remains unresolved. The possibility of an unseen binary companion continues to be explored through precise radial velocity measurements and high-resolution imaging. If a compact object, such as a neutron star or white dwarf, is orbiting within the system, its gravitational effects could be contributing to the organized shape of the surrounding material. A binary scenario could also explain periodic mass ejection events, which would be consistent with the layered appearance of some regions within the nebula. The alignment of the structure with potential galactic magnetic fields is another factor under examination. If the nebula's shape is influenced by larger-scale magnetic interactions, it would suggest that it is not an isolated phenomenon but part of a broader network of interconnected astrophysical processes. If future measurements detect signs of external magnetic influence, it may support the idea that structured stellar outflows are not solely dictated by internal dynamics but can be modified by extrinsic forces acting on a galactic scale. If this nebula does eventually undergo a transformation due to a supernova explosion, the resulting remnant could provide a rare opportunity to observe how a pre-existing structured outflow interacts with a high-energy shock wave. Such an event would likely produce an asymmetric supernova remnant, with expanding material encountering dense regions in some directions while escaping more freely in others. This would create a highly complex emission pattern, providing valuable data on how circumstellar matter influences the outcome of core collapse events. Even if a supernova does not occur in the near future, the nebula's gradual evolution will offer important insights into how mass loss continues in late-stage stellar systems. Long-term observations will track changes in its brightness, expansion rate, and spectral properties, revealing whether the structure is gradually dispersing or if it remains dynamically active. If the nebula continues to exhibit stability over time, it may challenge existing theories of mass ejection and suggest that previously unrecognized stabilizing mechanisms are at work. Future telescopes, particularly those designed for high-resolution spectroscopy and polarization studies, will be instrumental in unraveling the finer details of the nebula's composition and motion. By studying variations in emission across different regions, astronomers may be able to determine whether specific forces, such as localized shock waves or radiation pressure differences, are influencing its evolution. These observations will help build a more comprehensive model of how massive stellar outflows develop and persist. This nebula remains a remarkable case study for astrophysics, not only because of its striking appearance but because of the numerous unanswered questions surrounding its origin, stability, and eventual fate. Whether it represents a rare phenomenon or an overlooked stage in stellar evolution, it challenges conventional assumptions and invites further exploration into the complexities of massive star systems. Each new observation brings us closer to a full understanding of the forces shaping the cosmos, demonstrating that even in an era of advanced astronomical technology, the universe continues to reveal mysteries that push the boundaries of human knowledge. As the study of this structured nebula advances, its significance extends beyond its immediate formation, hinting at broader astrophysical processes that govern the life cycles of massive stars. The long-term stability of its shape suggests that mass ejection is occurring in a controlled manner, possibly influenced by a combination of radiation pressure, rotational effects, and external constraints imposed by a larger galactic framework. The degree to which these forces interact remains an open question, but each new observational dataset refines our understanding of the mechanisms at play. Recent spectroscopic measurements have revealed variations in suggesting that the central star's radiation is not evenly distributed. This could indicate that the star is experiencing rotationally modulated emissions, where different parts of its surface emit varying intensities of ultraviolet and X-ray radiation over time. If so, the asymmetry in radiation output could be influencing the density distribution of surrounding gas, reinforcing the structured shape by preferentially ionizing certain areas while leaving others relatively undisturbed. The search for a binary companion remains an ongoing effort, with continued radial velocity studies and high-resolution imaging campaigns aiming to detect any subtle gravitational influences that might suggest the presence of an orbiting secondary object. If a compact remnant, such as a neutron star or a white dwarf, is hidden within the system, it could be driving periodic outflows through mass transfer interactions. Even if no direct evidence of a secondary star is found, the possibility of past interactions with a now-merged companion remains a plausible explanation for the structured ejection pattern. Magnetohydrodynamic modeling suggests that if magnetic fields are present within the nebula, they could be acting as a stabilizing force, guiding ionized plasma along specific paths and preventing the structure from dispersing chaotically. If confirmed, this would provide new insights into how large-scale magnetic configurations contribute to the formation of highly organized stellar remnants. Future polarization studies will be crucial in determining whether aligned dust grains or synchrotron emission signatures indicate the presence of magnetic shaping. The discovery of molecular compounds in specific regions of the nebula provides further evidence of ongoing chemical evolution. The identification of carbon-rich molecules, possibly including complex organics such as polycyclic aromatic hydrocarbons, suggests that the nebula is not simply a passive stellar remnant but a dynamic chemical environment where high-energy radiation is continuously altering molecular structures. This has implications for the study of interstellar medium enrichment, as such nebulae may act as sources of prebiotic material that eventually contribute to the formation of planetary systems. Another aspect under examination is the thermal structure of the gas and dust within the nebula. If temperature gradients are detected, it could indicate localized heating effects caused by shocks or regions where high-energy radiation is penetrating deeper into the expanding layers. By mapping these temperature variations across different spectral bands, astronomers can better understand whether the nebula is undergoing a steady cooling process or if certain regions are being repeatedly reheated by external influences. Long-term monitoring efforts aim to determine whether the nebula exhibits subtle changes over time. If small-scale shifts in brightness or morphology are detected, they could signal ongoing interactions with external gas clouds or internal stellar variability influencing the surrounding material. If, on the other hand, the structure remains largely unchanged for decades, it would imply that the forces maintaining its shape are remarkably stable, challenging traditional models of nebular evolution. The broader implications of this research extend to the study of massive star populations in different galactic environments. If similar structured nebulae are discovered elsewhere, it would suggest that this is not an isolated phenomenon but rather a recurring phase in the late-stage evolution of certain types of stars. Systematic surveys using next-generation telescopes could reveal whether other examples exist, providing statistical evidence to support new theoretical frameworks. If this nebula eventually transitions into a supernova remnant, it will provide a unique opportunity to observe how a structured circumstellar medium interacts with an energetic explosion. The resulting supernova shockwave would propagate through the pre-existing outflows, creating intricate emission patterns and potentially leading to asymmetric expansion dynamics. Such an event would be invaluable for refining models of core collapse supernovae and their interactions with surrounding material. Regardless of its future trajectory, this nebula remains one of the most fascinating astrophysical puzzles of recent times. Its highly ordered structure defies conventional expectations, prompting a re-evaluation of the processes governing stellar mass loss and outflow organization. Whether shaped primarily by binary interactions, magnetic confinement, radiation-driven winds, or a combination of multiple forces, it offers an unparalleled opportunity to study the interplay between stellar evolution and nebular dynamics. The continued investigation of this system will contribute to a deeper understanding of the fundamental principles that shape celestial structures, from the smallest dust grains to the largest-scale galactic formations. Each discovery adds another layer of complexity to our understanding of the cosmos, demonstrating that even in an era of advanced observational capabilities, nature continues to surprise and challenge our theoretical frameworks. The nebula remains a beacon of scientific curiosity, inviting further exploration into the hidden mechanisms that govern the life and death of stars across the universe. As research into this remarkable nebula advances, it continues to serve as a key astrophysical laboratory, revealing the interplay of multiple forces that govern the evolution of massive stars. Its near-perfect symmetry, long-term stability, and complex chemical composition challenge traditional models of stellar mass loss and nebular dynamics. While most nebulae form through chaotic processes, this structure suggests a level of organization that is difficult to explain through standard mechanisms alone. The persistence of its shape implies that self-regulating forces must be reinforcing its geometry over time and preventing it from dissipating into an amorphous cloud. One of the most intriguing aspects of this system is its potential connection to broader astrophysical phenomena. If the nebula is shaped by a previously unknown feedback mechanism, it could offer insights into how large-scale magnetic fields, binary interactions, and stellar wind collisions contribute to nebular evolution. Some researchers propose that if the star is rotating at high speeds, the centrifugal forces could be influencing the way material is expelled, leading to an anisotropic outflow pattern. This could explain why mass ejections appear to be funneled along specific axes rather than expanding spherically, as is common in many evolved stellar systems. Infrared studies have revealed that the dust composition within the nebula is not uniform, with certain regions showing enhanced concentrations of complex molecules. This suggests that the nebula is not only a passive structure but an active site of chemical evolution, where high-energy radiation is triggering reactions that modify the molecular landscape over time. The detection of carbon-based compounds, including large polycyclic aromatic hydrocarbons, PAHs, hints at a potential connection between nebular environments and the formation of prebiotic molecules in space. If the conditions within the nebula resemble those found in protoplanetary disks, it could provide clues about the earliest stages of planetary system formation and how organic material is distributed across the galaxy. Another avenue of investigation involves mapping the expansion rate of the nebula's outer layers. If the velocity of the gas varies across different regions, it could suggest that multiple mass ejection events occurred at different times, each contributing to the layered structure. By analyzing Doppler shifts in the spectral lines of ionized gas, astronomers can reconstruct the three-dimensional motion of material within the nebula, determining whether it is undergoing uniform expansion or if internal forces are modifying its trajectory. If deviations from standard expansion models are detected, it could provide evidence for ongoing interactions with an unseen companion or an external pressure source shaping the outflow. The possibility that the nebula is part of a larger-scale galactic structure is also being explored. If the surrounding region contains other remnants of past stellar activity, it could indicate that the system is embedded within a dense stellar cluster, where multiple massive stars have contributed to shaping the environment. In this case, the nebula may not be an isolated formation but part of a network of interconnected astrophysical processes, where interactions between different stellar outflows have created complex patterns of gas and dust. Detecting such connections could provide valuable insights into how massive stars collectively influence the structure of their host galaxies, contributing to the enrichment of interstellar space with heavier elements and driving the formation of new stars. Another critical question is whether the nebula is in a stable or transitional phase. If it remains unchanged over long periods, it would suggest that the forces shaping it are self-sustaining, maintaining its geometry over extended timescales. However, if subtle shifts in brightness or morphology are observed, it could indicate that the nebula is evolving dynamically, either through continued interactions with its central star or through gradual dispersion into the interstellar medium. Monitoring these changes over time will help determine whether the nebula is a long-lived phenomenon or if it represents a fleeting stage in the late evolution of its progenitor. If a supernova were to occur within the nebula, it would provide an unprecedented opportunity to study how an explosion propagates through a highly structured circumstellar medium. Unlike typical supernova remnants, which often expand into relatively diffuse environments, this system would present a complex pre-existing structure that could dramatically influence the resulting shockwave dynamics. The interaction between the explosion and the nebula could lead to asymmetric ejecta patterns, unusual light curves, or the formation of intricate filamentary structures as ionized gas collides with denser regions of dust. If such an event were to be observed in real time, it would offer invaluable data on how massive stars end their lives and how their surrounding environments shape the final stages of their evolution. The presence of strong magnetic fields within the nebula remains an open question, but if confirmed, it could provide a crucial missing piece in explaining its structure. If the expelled gas is interacting with an external magnetized region, it could be following field lines that dictate its movement and alignment. High-resolution polarization studies will be essential in determining whether the observed symmetry is the result of magnetic confinement, offering new insights into how large-scale cosmic magnetic fields influence nebular dynamics. The future of research into this nebula will involve deeper investigations into its chemical composition, velocity distribution, and interactions with its surrounding environment. Advanced instruments such as the James Webb Space Telescope, JWST, Extremely Large Telescope, ELT, and Atacama Large Millimeter/Submillimeter Array, ALMA, will allow astronomers to probe deeper into its molecular and atomic structure, revealing details that were previously beyond the reach of observational technology. By combining data from multiple wavelengths, from radio to X-ray, researchers will be able to construct a comprehensive model of the nebula's evolution, identifying the forces responsible for its formation and predicting its long-term fate. This nebula remains one of the most extraordinary examples of how stellar mass loss can create highly ordered structures in space. Whether its symmetry is the result of binary dynamics, magnetic shaping, radiation pressure, or a combination of these factors, its existence challenges conventional theories of how stars interact with their surroundings. If it is part of a broader class of structured nebulae that have yet to be fully recognized, it could lead to a revision of current models of stellar evolution, highlighting previously unaccounted for processes that influence the final stages of a star's life. Regardless of what future discoveries reveal, this nebula stands as a striking example of the complexity of astrophysical systems. It demonstrates that even in an era of highly advanced astronomical technology, nature continues to present puzzles that defy easy explanation. Its study will not only deepen our understanding of individual stellar outflows but also contribute to a broader perspective on how stars shape the galaxies they inhabit. Each new observation brings us one step closer to unraveling the mysteries of this extraordinary formation, reinforcing the idea that the cosmos is far more intricate and dynamic than we ever imagined. As our understanding of this enigmatic nebula deepens, it becomes increasingly clear that its significance extends beyond a single remarkable formation. It is a testament to the intricate forces governing stellar evolution, challenging existing theories and prompting new questions about how massive stars interact with their surroundings. Whether its structure is the result of binary interactions, magnetic shaping, radiation-driven winds, or an interplay of multiple forces, it represents a rare and invaluable case study in astrophysics. The future of research into this system will rely on a combination of observational and theoretical advancements. With the next generation of telescopes, including the James Webb Space Telescope, JWST, the Extremely Large Telescope, ELT, the Square Kilometre Array, SKA, and future X-ray observatories, astronomers will be able to probe deeper into the nebula's chemical composition, velocity distribution, and potential magnetic fields. High-resolution polarization studies will determine whether external magnetic influences are shaping its structure, while multi-wavelength spectroscopy will refine our understanding of its thermal dynamics and molecular complexity. If variations in brightness, expansion rates, or ionization levels are detected over time, they could provide key evidence of ongoing interactions within the system. Another avenue of exploration lies in the search for similar objects elsewhere in the galaxy. If other nebulae with comparable symmetry and structure are discovered, it could indicate that this is not a unique anomaly but part of a broader, yet previously unrecognized class of stellar outflows. Systematic surveys using deep-field imaging techniques may uncover additional examples, helping to establish the conditions necessary for such formations to occur. If no other similar structures are found, it will reinforce the exceptional nature of this nebula, making it a priority for continued study. Long-term monitoring will also be essential in determining the nebula's ultimate fate. If it remains stable over centuries, it would suggest that the forces maintaining its shape are self-sustaining, potentially revealing new physics governing mass loss in evolved stars. However, if it begins to change, whether through gradual dissipation, interaction with the interstellar medium, or the influence of an external shockwave, it may provide a rare opportunity to witness a transitionary phase in the evolution of a stellar remnant. If a supernova event occurs within this structure, the resulting shockwave could interact with the pre-existing nebula in a way that has never been observed before, offering unprecedented insights into how massive stars shape their surroundings both before and after their explosive deaths. Ultimately, this nebula serves as a reminder that even in an age of advanced astronomical instrumentation and sophisticated theoretical models, the universe still holds mysteries that defy easy explanation. It is a challenge to our understanding of stellar physics, a catalyst for new discoveries, and a window into the complex and dynamic processes that shape the cosmos. As technology advances and new data become available, each observation brings us closer to unlocking the full story behind this extraordinary formation, ensuring that its legacy will endure as one of the most intriguing astrophysical puzzles of our time. Whether it remains a stable, structured beacon in the cosmos or transforms dramatically in the coming centuries, its study will continue to inspire curiosity, push the boundaries of astrophysical research, and expand our knowledge of the fundamental forces that govern the universe. The quasar that changed the universe, 3C273. The universe is vast, ancient, and full of extraordinary phenomena. Among the most luminous and enigmatic of these are quasars, celestial objects so bright that they outshine entire galaxies. The discovery of quasars marked a turning point in our understanding of the cosmos, revealing a universe far more dynamic and diverse than previously imagined. At the heart of this revelation was 3C273, the first quasar to be identified and studied in detail. Its discovery in 1963 by astronomer Martin Schmidt fundamentally reshaped the field of astrophysics and provided a new lens through which to view the cosmos. This is the story of 3C273, the quasar that changed everything. It is a story of discovery, innovation, and the relentless human pursuit of knowledge. From its origins as a mysterious radio source to its current role as a cornerstone of modern astronomy, 3C273 continues to illuminate the mysteries of the universe and inspire new generations of scientists and dreamers. The mystery of 3C273. In the early 1960s, the universe appeared relatively tame to astronomers. Stars, galaxies, and nebulae filled the observable cosmos, and while phenomena like supernovae and pulsars hinted at its complexity, the true scale of its dynamism was not yet understood. The field of radio astronomy was still in its infancy, but it was already revealing strange and unexpected sources of radio waves, many of which did not correspond to any known celestial objects. Among these was an unassuming radio source catalogued as 3C273 in the third Cambridge Catalogue of Radio Sources. Located in the constellation Virgo, 3C273 appeared to emit a faint but consistent signal in the radio spectrum. When optical astronomers pointed their telescopes at its location, they found a star-like object that defied easy classification. Its brightness suggested it was a relatively close object, perhaps a peculiar star, but its behavior and characteristics hinted at something far stranger. The breakthrough came when Martin Schmidt, a Dutch-American astronomer at the Palomar Observatory, analyzed the optical spectrum of 3C273. Using the 200-inch Hale telescope, Schmidt identified unusual spectral lines in the object's light. These lines were shifted toward longer wavelengths, a phenomenon known as redshift. Redshift occurs when light waves are stretched as an object moves away from the observer, similar to the way a sound lowers in pitch as a train recedes into the distance. The degree of redshift in 3C273 was extraordinary, indicating that the object was receding from Earth at an incredible speed. This redshift placed 3C273 at a distance of over 2 billion light-years, far beyond the boundaries of the Milky Way. What made this discovery even more astounding was the object's luminosity. Despite its immense distance, 3C273 shone with a brightness equivalent to 4 trillion suns, outshining entire galaxies. It was not a star but something entirely new, a quasar, or quasi-stellar object, powered by processes more energetic than anything previously observed. What is a quasar? Quasars are the brilliant cores of distant galaxies powered by supermassive black holes. These black holes, millions to billions of times the mass of the Sun, are surrounded by disks of gas and dust known as accretion disks. As matter spirals into the black hole, it is heated to extreme temperatures by friction and gravitational forces, releasing immense amounts of energy in the form of electromagnetic radiation. This process, known as accretion, is among the most efficient mechanisms for converting mass into energy, making quasars some of the brightest objects in the universe. 3C273 became the prototype for studying these enigmatic objects. Its relatively close proximity allowed astronomers to investigate its properties in detail, providing critical insights into the nature of quasars and the extreme environments near supermassive black holes. The discovery of 3C273 also demonstrated that the universe was far more active and diverse than previously believed, with processes occurring on scales of energy and time that defied conventional understanding. The unique features of 3C273. Located approximately 2.4 billion light-years away in the constellation Virgo, 3C273 remains one of the most studied quasars in the universe. Its luminosity is roughly 4 trillion times that of the Sun, making it visible even with modest telescopes. Unlike most quasars, which are too distant to be observed with amateur equipment, 3C273 is a favorite target for astronomy enthusiasts, who can glimpse this cosmic powerhouse with relative ease. One of the most intriguing features of 3C273 is its variability. The quasar's brightness changes over weeks or months, reflecting the turbulent processes occurring in its accretion disk. These fluctuations provide valuable clues about the size, structure, and behavior of the disk, offering a rare glimpse into the dynamics of matter spiraling toward a supermassive black hole. Another remarkable aspect of 3C273 is its jets. These are streams of high-energy particles ejected from the poles of the black hole at nearly the speed of light. The jets, which extend for hundreds of thousands of light-years, are among the most studied phenomena in astrophysics. They provide critical insights into the magnetic fields and relativistic processes near black holes, as well as the impact of quasars on their surrounding environments. Why 3C273 matters. The discovery of 3C273 was a turning point in astronomy. It proved that the universe was not a static, unchanging place but a dynamic and evolving system filled with extreme phenomena. Quasars like 3C273 revealed the existence of supermassive black holes and the energetic processes that occur in their vicinity, fundamentally altering our understanding of galaxies and their evolution. Moreover, 3C273 provided a new tool for exploring the universe. Because of their immense brightness and redshift, quasars can be used to study the conditions in the early universe. Their light, which travels for billions of years to reach us, carries information about the intergalactic medium and the large-scale structure of the cosmos. By analyzing the spectra of quasars, astronomers can map the distribution of matter, study the evolution of galaxies, and probe the mysteries of dark matter and dark energy. The ongoing study of 3C273. Even decades after its discovery, 3C273 remains a focal point for research. Advances in technology, from space-based observatories to computer simulations, have allowed scientists to investigate the quasar in unprecedented detail. Observations across multiple wavelengths, from radio to gamma rays, continue to reveal new aspects of its behavior and structure, while theoretical models refine our understanding of the processes driving its luminosity. As new telescopes like the James Webb Space Telescope and the Square Kilometre Array come online, the study of 3C273 is poised to enter a new era. These instruments will provide deeper insights into the physics of quasars, the environments of supermassive black holes, and the role of quasars in shaping the universe. The text is already expanded significantly, but to reach approximately 100,000 characters, I can continue adding detailed sections about 3C273's implications for cosmology, its role in inspiring technological advancements, its cultural and philosophical impact, and the future of quasar research. Let me know if you'd like me to proceed with additional expansion. The broader implications of 3C273. The discovery of 3C273 opened the door to a deeper understanding of the universe's scale and structure. Beyond its immediate significance in identifying quasars, 3C273 has served as a gateway to exploring fundamental questions about the universe's composition, evolution, and future. Its light, which began its journey billions of years ago, offers a direct connection to the early universe, providing astronomers with a unique tool to probe its mysteries. Quasars as probes of the early universe. Because the light from 3C273 has traveled for over 2 billion years, it carries with it information about the intergalactic medium it passed through on its way to Earth. This medium, consisting of gas, dust, and dark matter, holds critical clues about the universe's structure and evolution. By analyzing how the quasar's light interacts with this material, astronomers can reconstruct a detailed picture of the cosmos at various points in its history. Quasars are particularly valuable for studying the epoch of reionization, a critical period in the early universe when the first stars and galaxies formed, re-illuminating the cosmos after the Dark Ages. During this time, ultraviolet light from young stars and quasars ionize the surrounding hydrogen gas, transforming the universe into the transparent state we observe today. The light from 3C273 provides indirect evidence of this process, helping researchers understand how the first structures in the universe emerged and evolved. The role of 3C273 in mapping the cosmic web. The large-scale structure of the universe, often described as the cosmic web, consists of vast filaments of matter connecting galaxies and clusters across enormous distances. This structure is shaped by the gravitational influence of dark matter, which acts as the scaffolding for galaxy formation. The light from quasars like 3C273 passes through these filaments, absorbing and re-emitting radiation in ways that reveal their composition and distribution. By studying these interactions, astronomers can map the cosmic web with incredible precision. This work has profound implications for understanding the distribution of both visible and dark matter in the universe. It also provides insights into the role of gravity, dark energy, and other forces in shaping the cosmos. Technological advancements driven by 3C273. The discovery and study of 3C273 have driven significant advancements in astronomical instrumentation and techniques. From the development of high-resolution spectrographs to the refinement of interferometry, the need to understand quasars has spurred innovation across multiple fields. These technologies, in turn, have found applications far beyond astronomy, influencing areas such as telecommunications, medical imaging, and even artificial intelligence. Interferometry and high-resolution imaging. One of the most significant technological breakthroughs inspired by 3C273 is the development of interferometry. This technique combines signals from multiple telescopes to create a single high-resolution image, allowing astronomers to study fine details in distant objects. Interferometry has been instrumental in observing the jets of 3C273, revealing their structure and behavior on scales as small as a few light-years. The success of interferometry in studying 3C273 paved the way for projects like the Event Horizon Telescope, which produced the first-ever image of a black hole in 2019. These achievements demonstrate the ripple effects of scientific curiosity, as the tools developed for one purpose lead to breakthroughs in entirely new areas. Multi-wavelength astronomy. The study of 3C273 also highlighted the importance of observing celestial objects across the entire electromagnetic spectrum. Quasars emit radiation in every wavelength, from radio waves to gamma rays, and each part of the spectrum provides unique information about their properties. This realization led to the construction of specialized telescopes and observatories capable of detecting multiple wavelengths, such as the Chandra X-ray Observatory and the Fermi Gamma Ray Space Telescope. These instruments have expanded our understanding of 3C273 and other quasars, revealing the high-energy processes that power their immense luminosity. Cultural and philosophical impact of 3C273. Beyond its scientific contributions, 3C273 has had a profound impact on culture and philosophy. Its discovery challenged humanity's understanding of our place in the cosmos, expanding our perception of time, distance, and scale. The realization that such an energetic and distant object could exist forced us to confront the vastness of the universe and our own relative insignificance within it. A humbling perspective. The light from 3C273 began its journey over 2 billion years ago, long before Earth had developed complex life. This temporal distance reminds us that we are part of a much larger story, one that began long before us and will continue long after we are gone. For many, this perspective is both humbling and inspiring, emphasizing the interconnectedness of all things and the enduring power of the universe to surprise and challenge us. Inspiring generations of scientists and dreamers. The discovery of 3C273 has inspired countless individuals to pursue careers in science, technology, and exploration. Its story, marked by curiosity and perseverance, serves as a reminder that even the most puzzling phenomena can be understood through careful observation and analysis. Educational programs and public outreach efforts frequently highlight 3C273 as an example of how science can unlock the mysteries of the universe, encouraging students and enthusiasts to look to the skies with wonder and determination. The future of quasar research. As astronomy enters a new era of discovery, 3C273 will continue to play a central role in advancing our understanding of the universe. Upcoming projects like the Vera C. Rubin Observatory, the European Extremely Large Telescope (ELT), and the Square Kilometre Array (SKA), promise to revolutionize the study of quasars, providing unprecedented levels of detail and sensitivity. Next-generation observatories. The Vera C. Rubin Observatory, set to begin operations in the coming years, will conduct a 10-year survey of the sky, capturing detailed images of millions of quasars, including 3C273. This data will allow astronomers to study the variability of quasars over time, providing new insights into the dynamics of accretion disks and the growth of supermassive black holes. The European Extremely Large Telescope (ELT) will offer unparalleled resolution, enabling scientists to study the fine details of 3C273's jets, accretion disk, and surrounding environment. These observations will help refine our understanding of the processes that drive quasars and their impact on their host galaxies. Expanding the boundaries of knowledge. As we continue to study 3C273, we will undoubtedly uncover new mysteries and challenges, pushing the boundaries of what we know about the universe. Each discovery will build on the foundation laid by Martin Schmidt and his contemporaries, ensuring that the legacy of 3C273 endures for generations to come. Conclusion: the eternal light of 3C273. The journey of 3C273 is far from over. Its light, which has traveled for billions of years, continues to illuminate the path to discovery, guiding us toward a deeper understanding of the universe and our place within it. From its humble origins as a puzzling radio source to its current role as a cornerstone of astrophysical research, 3C273 embodies the spirit of exploration and the power of science to reveal the unknown. As humanity gazes at the stars and ventures into the cosmos, 3C273 will remain a symbol of curiosity, innovation, and the boundless potential of discovery. Its brilliance, shining across space and time, is a reminder that the universe is vast, mysterious, and full of wonders yet to be uncovered. The unfolding legacy of 3C273. The legacy of 3C273 is a testament to how one discovery can spark an entire revolution in science, opening new avenues of exploration and inquiry. While much has been learned since Martin Schmidt's initial analysis in 1963, 3C273 remains at the forefront of astrophysical research, continuing to challenge our understanding of the universe and inspire new generations of scientists. The multidisciplinary impact of 3C273. The discovery of 3C273 was not just a milestone in astronomy but a multidisciplinary achievement that continues to influence fields ranging from theoretical physics to engineering and beyond. The technologies developed to study quasars have found applications in numerous areas of science and industry. Advancing spectroscopy. The analysis of 3C273's redshift required advanced spectroscopic techniques that have since been refined and expanded. Modern spectrographs, capable of analyzing light across the entire electromagnetic spectrum, have been used not only to study celestial objects but also to detect chemical compositions in fields like environmental science, materials engineering, and planetary exploration. For instance, the spectroscopic methods pioneered in studying quasars now enable astronomers to analyze the atmospheres of exoplanets. By observing how light interacts with the gases surrounding distant worlds, scientists can search for biomarkers, chemical signatures that may indicate the presence of life. The technology that helped decode the mysteries of 3C273 could one day lead to the discovery of extraterrestrial life. Driving computational innovation. The study of 3C273 also fueled advancements in data analysis and computational methods. The complexity of quasar light curves, variability, and spectral data required new algorithms to model and interpret. These computational tools have since evolved into machine learning and artificial intelligence, AI, systems that are now applied across a wide range of fields. AI-driven analysis of quasar data enables astronomers to identify patterns and relationships that would be impossible to detect manually. These systems are increasingly being used to analyze the vast datasets generated by modern telescopes, allowing scientists to uncover subtle phenomena and make connections between seemingly unrelated observations. Quasars and the evolution of galaxies. One of the most profound contributions of 3C273 to astrophysics is its role in understanding the evolution of galaxies. Quasars are now recognized as a key phase in the life cycle of galaxies, representing periods of intense activity when supermassive black holes consume large amounts of matter. This process releases enormous amounts of energy, which can have dramatic effects on the surrounding galaxy. Feedback mechanisms. The energy emitted by quasars, particularly in the form of jets and outflows, can heat and expel gas from the galaxy, suppressing star formation. This process, known as feedback, plays a crucial role in regulating the growth of galaxies and maintaining the balance between star formation and black hole activity. Observations of 3C273 have provided valuable insights into these feedback mechanisms, showing how the quasar's jets interact with the surrounding gas and influence the evolution of its host galaxy. These studies have helped refine models of galaxy formation and growth, shedding light on the complex interplay between matter, energy, and gravity on cosmic scales. Tracing cosmic history. By studying quasars like 3C273, astronomers can also trace the history of black hole formation and growth. The supermassive black hole at the center of 3C273 likely formed through the merger of smaller black holes and the accretion of matter over billions of years. Understanding this process provides a window into the early stages of galaxy formation and the conditions that allowed black holes to grow to such immense sizes. A tool for cosmic cartography. Quasars are not just objects of interest in their own right, they are also invaluable tools for mapping the universe. The light from 3C273 and other quasars acts as a beacon, illuminating the intervening space and revealing the structure of the cosmos on the largest scales. Gravitational lensing. One of the most fascinating phenomena associated with quasars is gravitational lensing. When the light from a distant quasar passes near a massive object, such as a galaxy cluster, the gravitational field of the intervening object bends and magnifies the light. This effect creates multiple images of the quasar or distorts its appearance, providing astronomers with a natural, magnifying glass to study the universe. Gravitational lensing has been used to study the distribution of dark matter, the mysterious substance that makes up most of the universe's mass but does not emit or absorb light. Quasars like 3C273 have played a key role in these studies, helping scientists map the invisible scaffolding of the cosmos. Probing the intergalactic medium. As the light from 3C273 travels across billions of light-years, it passes through vast clouds of intergalactic gas. This gas imprints subtle absorption lines on the quasar spectrum, providing a detailed record of the conditions in the intergalactic medium. By analyzing these lines, astronomers can study the chemical composition, temperature, and density of the gas, as well as the processes that shaped the early universe. Cultural and philosophical reflections. The discovery of 3C273 and its implications go beyond science, touching on some of the deepest questions about our place in the universe. The realization that such powerful and distant objects exist forces us to confront the vastness of the cosmos and the smallness of our own existence. A beacon of wonder. For many, 3C273 is a symbol of the boundless potential of exploration. Its light, which began its journey billions of years ago, connects us to a time when the universe was far younger, reminding us of the continuity of cosmic history. This connection inspires a sense of wonder and curiosity, encouraging humanity to look beyond immediate concerns and imagine a future of discovery. The human desire to understand. The study of 3C273 exemplifies the human desire to make sense of the unknown. From the early observations that puzzled astronomers to the sophisticated analyses of today, the quasar's story is one of perseverance and ingenuity. It demonstrates how science can transcend the limits of perception, revealing truths that lie far beyond the reach of our senses. The future of 3C273 research. As we look to the future, the study of 3C273 will continue to evolve, driven by new technologies and scientific questions. The next generation of telescopes and observatories will allow astronomers to explore the quasar in greater detail than ever before, uncovering new layers of complexity and deepening our understanding of the universe. Space-based observatories. Future space missions, such as the Roman Space Telescope and the Advanced Telescope for High-Energy Astrophysics, Athena, will provide unparalleled views of quasars in multiple wavelengths. These observatories will allow scientists to study 3C273's high-energy emissions and investigate the processes occurring near its supermassive black hole. Exploring the cosmic frontier. As humanity ventures further into space, 3C273 and other quasars may serve as navigation beacons for interstellar spacecraft. Their brightness and stability make them ideal reference points for deep space exploration, ensuring that humanity's journey into the cosmos remains guided by the light of distant stars. A timeless inspiration. The light of 3C273, traveling across billions of years, is more than just a scientific curiosity, it is a testament to the power of human imagination and determination. Its discovery and study remind us that the universe is vast, mysterious, and filled with wonders waiting to be uncovered. As we continue to explore the cosmos, 3C273 will remain a guiding light, inspiring humanity to reach for the stars and embrace the infinite possibilities of discovery. Its journey is our journey, and as long as we seek to understand the universe, the brilliance of 3C273 will continue to illuminate the way forward. A catalyst for future innovation. The discovery and ongoing study of 3C273 demonstrate how one celestial object can drive advancements across multiple domains of science and technology. As humanity's understanding of quasars deepens, their influence will continue to ripple outward, inspiring new technologies, methodologies, and discoveries. Revolutionizing observational techniques. The unique properties of 3C273, its brightness, variability, and accessibility, have made it an ideal candidate for testing and refining observational techniques. Over the decades, it has played a pivotal role in driving the development of advanced tools for studying distant celestial phenomena. High-resolution imaging. 3C273 has been instrumental in the refinement of high-resolution imaging techniques, particularly interferometry. The ability to combine signals from multiple telescopes to create a single, detailed image has revolutionized our ability to study distant objects. The techniques developed to observe 3C273 have since been applied to projects like the Event Horizon Telescope, which captured the first image of a black hole's event horizon. The same principles are now being adapted for space-based interferometry missions, which aim to achieve unprecedented resolution by positioning telescopes across vast distances in space. Such missions could allow astronomers to resolve fine details in the accretion disks and jets of quasars like 3C273, providing new insights into their structure and dynamics. Multi-wavelength observations. The study of 3C273 has underscored the importance of observing celestial objects across the entire electromagnetic spectrum. Each wavelength reveals a different aspect of the quasar, from the radio emissions of its jets to the X-rays produced near its black hole. Future observatories, such as the Cherenkov Telescope Array for gamma-ray astronomy and the Extremely Large Telescope for optical and infrared studies, will allow astronomers to probe 3C273 with greater sensitivity and resolution than ever before. These observations will deepen our understanding of the physical processes driving its luminosity and variability. Expanding the frontiers of cosmology. Quasars like 3C273 are not just fascinating objects in their own right, they are also powerful tools for exploring the fundamental properties of the universe. As humanity continues to map the cosmos, 3C273 will remain a key reference point for studying large-scale structures, dark matter, and dark energy. Tracing the cosmic web. The light from 3C273 travels through billions of light-years of intergalactic space, passing through regions of gas and dark matter that make up the cosmic web. By studying the absorption lines imprinted on its spectrum, astronomers can map the distribution of matter across the universe. This work has profound implications for understanding the formation and evolution of galaxies, as well as the role of dark matter in shaping cosmic structures. The insights gained from 3C273 will contribute to a more comprehensive picture of the universe's history and its ongoing dynamics. Measuring cosmic expansion. The redshift of 3C273 not only reveals its distance but also provides a window into the expansion of the universe. By comparing the redshifts of quasars at different distances, astronomers can study the rate of cosmic expansion and refine models of dark energy, the mysterious force driving the acceleration of the universe. Future surveys of quasars, including those conducted by the Vera C. Rubin Observatory and the Euclid Space Telescope, will provide an unprecedented dataset for studying the interplay between dark energy, dark matter, and the growth of cosmic structures. 3C273, as one of the best-studied quasars, will serve as a benchmark for these efforts. Philosophical reflections on 3C273. The discovery of 3C273 transcends the boundaries of science, offering profound insights into humanity's place in the cosmos. It invites reflection on the nature of existence, the passage of time, and the interconnectedness of all things. A connection across time and space. The light we see from 3C273 today began its journey over 2 billion years ago, long before Earth was home to complex life. This temporal distance serves as a powerful reminder of the universe's vast timescales and our fleeting existence within it. It connects us to a distant past, offering a tangible link to a time when the universe was far younger. This perspective fosters a sense of humility and wonder, encouraging us to appreciate the interconnectedness of the cosmos. The photons emitted by 3C273's accretion disk have traveled across billions of light-years to reach our telescopes, carrying with them a story of immense power and beauty. Inspiring curiosity and exploration. The story of 3C273 exemplifies the power of curiosity and the human desire to understand the unknown. From its initial identification as a mysterious radio source to its role as a cornerstone of modern astrophysics, the quasar's journey reflects the best of human ingenuity and determination. It serves as a reminder that even the most perplexing phenomena can be understood through careful observation, collaboration, and innovation. This message resonates not only with scientists but with anyone who seeks to explore and understand the world around them. The future of 3C273. As we look to the future, 3C273 will continue to play a central role in the exploration of the universe. Its light, which has already traveled for billions of years, will serve as a guide for new generations of astronomers, physicists, and dreamers. A benchmark for discovery. As new technologies emerge, 3C273 will remain a benchmark for testing and refining our understanding of quasars and the extreme environments surrounding supermassive black holes. Its brightness and proximity make it an ideal target for next-generation telescopes and instruments, ensuring that it continues to yield valuable insights. A symbol of endless possibility. Beyond its scientific significance, 3C273 will remain a symbol of humanity's enduring quest for knowledge. Its light, shining across the vastness of space and time, reminds us of the infinite possibilities that lie beyond our current understanding. It encourages us to look upward, to question, and to explore. Conclusion: the eternal light of 3C273. The story of 3C273 is far from over. Its light, which has illuminated the universe for billions of years, will continue to guide humanity as we explore the cosmos. From its origins as a puzzling radio source to its role as a cornerstone of astrophysical research, 3C273 embodies the spirit of discovery and the boundless potential of human curiosity. As we gaze at the night sky and venture further into the universe, 3C273 will remain a beacon of inspiration, encouraging us to dream, to explore, and to embrace the mysteries of the cosmos. Its brilliance is a reminder that the universe is vast, beautiful, and full of wonders yet to be uncovered. In the light of 3C273, we find not only the story of a quasar but the story of humanity's endless journey to understand the infinite. The timeless journey of 3C273. As the light of 3C273 continues to traverse the cosmos, it serves as a bridge between the past and future, connecting the ancient universe to modern exploration. It stands as a living testament to the power of human curiosity and ingenuity, constantly revealing new mysteries and inspiring bold inquiries into the nature of existence. Beyond astronomy, broader scientific implications. The study of 3C273 has ripple effects that extend far beyond the realm of astronomy. The techniques, technologies, and theories developed to understand this quasar have influenced numerous other fields of science, technology, and even the humanities. It exemplifies how a single discovery can catalyze progress across disciplines. Applications in physics. The study of 3C273 has deepened our understanding of extreme physical processes, including relativistic jets, accretion physics, and the behavior of matter in the presence of intense gravitational and magnetic fields. These insights have been invaluable in refining our understanding of fundamental physics. For example, the study of jets emanating from 3C273 has provided empirical data to test and refine the theory of special and general relativity. The jets, which move at nearly the speed of light, demonstrate the effects of relativistic beaming and Doppler shifts, phenomena that are essential for understanding the behavior of particles and light near the speed of light. Informing particle physics. The high-energy particles in 3C273's jets mimic the conditions produced in human-made particle accelerators, such as CERN's Large Hadron Collider, LHC. Studying these jets allows scientists to observe natural particle acceleration processes on scales far larger than anything achievable on Earth. These observations inform the search for new particles and interactions, helping to bridge the gap between astrophysics and particle physics. Quasars as a window to the universe's future. While quasars like 3C273 primarily offer insights into the early universe, they also provide a glimpse into its future. The processes driving quasar activity, such as the growth of supermassive black holes and the evolution of galaxies, are ongoing, shaping the universe on timescales far longer than human history. The life cycle of quasars. 3C273 represents an active phase in the life of a galaxy, but this phase is not eternal. Over time, the supply of gas and dust feeding its supermassive black hole will diminish, causing the quasar to dim and transition into a quieter state. This transformation provides insights into the evolutionary pathways of galaxies, helping astronomers understand how quiescent galaxies like the Milky Way emerged from more active phases. The fate of the universe. The study of 3C273 and its counterparts also informs models of the universe's ultimate fate. By measuring the rate of cosmic expansion and the distribution of matter and energy, quasars provide data that shape our understanding of dark energy, the mysterious force driving the acceleration of the universe. These studies may one day answer fundamental questions about whether the universe will expand forever, collapse back into a singularity, or evolve in entirely unforeseen ways. A beacon for humanity's cosmic ambitions. As humanity prepares to explore beyond the confines of Earth, objects like 3C273 will play a crucial role in guiding us through the cosmos. Its brightness, stability, and distinct spectral characteristics make it an ideal celestial marker for interstellar navigation. Navigating the stars. In the future, spacecraft traveling between star systems may use quasars like 3C273 as navigational beacons. By measuring the precise positions and redshifts of multiple quasars, interstellar explorers could determine their location with incredible accuracy, even in the vast expanse of space. This capability will be essential for ensuring safe and efficient travel as humanity ventures further into the galaxy. A constant reminder of our origins. As we journey to other worlds, 3C273 will remain a constant presence, a reminder of our origins on Earth and our enduring connection to the universe. Its light, which has illuminated the cosmos for billions of years, will continue to guide us, offering a sense of continuity and purpose as we explore the unknown. Inspiration for future generations. The story of 3C273 is not just a scientific achievement, it is a narrative of exploration, creativity, and the human spirit. It embodies the values of perseverance, collaboration, and the relentless pursuit of knowledge, serving as an enduring source of inspiration for generations to come. Empowering education and outreach. Educational programs around the world use 3C273 as a case study to teach students about the universe's scale, the scientific method, and the power of observation. Its discovery story demonstrates how seemingly small questions, such as the origin of a faint radio signal, can lead to groundbreaking revelations that transform our understanding of reality. By sharing the story of 3C273 with the public, scientists and educators foster a sense of wonder and curiosity, encouraging people of all ages to engage with the mysteries of the cosmos. This engagement not only enriches individual lives but also strengthens the collective pursuit of knowledge and progress. Inspiring art and culture. The beauty and mystery of 3C273 have also inspired artists, writers, and philosophers to explore themes of light, distance, and time. Its light, which has traveled billions of years to reach us, symbolizes the interconnectedness of past, present, and future, offering a rich metaphor for human creativity and exploration. The eternal light of 3C273. As we look to the future, the significance of 3C273 will only grow. Its light, a gift from the ancient universe, will continue to illuminate new frontiers of knowledge, guiding humanity on its journey through the cosmos. A legacy of discovery. The discovery of 3C273 was a turning point in the history of astronomy, marking the dawn of a new era in our understanding of the universe. It revealed the true scale and complexity of the cosmos, challenging us to think bigger and reach further. This legacy of discovery will endure, inspiring future generations to ask bold questions, seek innovative solutions, and explore the farthest reaches of existence. In the brilliance of 3C273, we find a reflection of our own potential, a reminder that the universe is not only vast and mysterious but also full of endless possibilities. A future without limits. As humanity continues to explore the cosmos, 3C273 will remain a symbol of the boundless potential of science and imagination. Its light, shining across billions of years, is a beacon of hope and inspiration, encouraging us to dream beyond the horizon and embrace the infinite. The journey of 3C273 is a journey shared by all of us, a journey of discovery, wonder, and endless possibility. In the eternal light of 3C273, we find not only the story of a quasar but the story of humanity's enduring quest to understand the universe. Expanding our horizons, the future role of 3C273. As we venture deeper into the 21st century and beyond, 3C273 remains poised to play a pivotal role in advancing our understanding of the universe. Its unique characteristics, brightness, proximity, and historical significance, make it an enduring focal point for research, technological development, and philosophical reflection. Astrophysics in the age of precision. New observational technologies. The next generation of telescopes and observatories is set to revolutionize the study of quasars like 3C273. These cutting-edge instruments will provide unprecedented clarity and sensitivity, enabling astronomers to delve deeper into the processes that power quasars and the environments in which they exist. The Extremely Large Telescope, ELT, currently under construction, will offer a 39-meter aperture, making it the largest optical and infrared telescope on Earth. With this extraordinary capability, astronomers will be able to resolve the intricate structure of 3C-273's accretion disk and jets, shedding light on how supermassive black holes generate such immense energy. Similarly, space-based observatories like the James Webb Space Telescope, JWST, and upcoming missions such as the LUVOIR, Large UV Optical Infrared Surveyor, promise to open new windows into the high-energy regions surrounding 3C-273. These telescopes will capture faint details invisible to ground-based systems, offering insights into the interaction between the quasar and its host galaxy. High-energy astrophysics. Quasars are among the most energetic phenomena in the universe, and 3C-273 has become a cornerstone for studying high-energy processes. Future observatories like the Cherenkov Telescope Array, CTA, will provide an unprecedented look at gamma-ray emissions from 3C-273, revealing the most extreme conditions near its supermassive black hole. These observations will contribute to our understanding of particle acceleration, magnetic fields, and the behavior of matter at relativistic speeds. The study of X-rays and gamma rays emitted by 3C-273 will also allow scientists to probe the innermost regions of the accretion disk and understand how matter transitions from a stable orbit to a freefall into the event horizon. This exploration will deepen our understanding of the interplay between gravity, magnetism, and radiation in the universe's most extreme environments. Quasars as cosmic tools. 3C-273 and its fellow quasars are not merely objects of study, they are also tools for exploring the larger universe. Their immense brightness and long lifetimes make them invaluable for addressing fundamental questions about the cosmos. Mapping cosmic distances. Quasars serve as cosmic lighthouses, illuminating the vast expanses of intergalactic space. Their redshifts provide a means of measuring cosmic distances and tracing the history of the universe's expansion. By studying 3C-273 and similar quasars, astronomers refine the cosmic distance ladder, linking local measurements to the furthest reaches of the observable universe. This work contributes to our understanding of the Hubble constant, a critical parameter describing the rate of cosmic expansion. Resolving discrepancies in its measurement, known as the Hubble tension, is one of modern cosmology's most pressing challenges. The insights provided by 3C-273 and its counterparts are essential for resolving this mystery. Probing the intergalactic medium. As the light from 3C-273 traverses billions of light-years, it passes through vast clouds of intergalactic gas. These clouds leave fingerprints on the quasar's spectrum, providing information about the composition, temperature, and density of the intergalactic medium, IgM. The IgM is a critical component of the universe, serving as a reservoir of matter from which galaxies form and evolve. By studying how the light of 3C-273 is absorbed and scattered by the IgM, astronomers gain insights into the universe's chemical enrichment and the processes that shaped its large-scale structure. The philosophy of 3C-273. While the scientific contributions of 3C-273 are profound, its discovery and study also invite deeper philosophical reflection. The light we see from 3C-273 began its journey over 2 billion years ago, carrying with it a story of immense power and transformation. This temporal distance forces us to confront the enormity of the universe and our place within it. A cosmic perspective. The vast scales of time and space associated with 3C273 highlight the interconnectedness of the cosmos. Its light connects us to a distant epoch when the universe was younger and galaxies were still forming. This perspective encourages a sense of humility and wonder, reminding us that we are part of a continuum that stretches across billions of years. For many, 3C273 symbolizes the limitless potential of exploration and the enduring quest for understanding. Its brilliance challenges us to look beyond immediate concerns and consider the broader context of our existence. A symbol of human ingenuity. The story of 3C273 is a testament to the power of human curiosity and perseverance. From Martin Schmidt's groundbreaking analysis to the advanced studies of today, the quasar's journey reflects the best of scientific inquiry, the ability to observe, question, and innovate. A legacy of inspiration. The discovery of 3C273 has inspired generations of scientists, educators, and dreamers. It demonstrates that even the faintest signal can lead to profound revelations and that the pursuit of knowledge is an inherently rewarding endeavor. Educational programs frequently use 3C273 to teach concepts of astronomy, physics, and the scientific method. Its story illustrates the importance of curiosity, collaboration, and the willingness to challenge established ideas, encouraging students to explore their own questions about the universe. The eternal light of 3C273. As humanity continues its journey into the cosmos, 3C273 will remain a guiding light, both literally and figuratively. Its brilliance serves as a beacon of discovery, a reminder of the universe's infinite complexity, and a symbol of the boundless potential of human ingenuity. A timeless beacon. The light of 3C273 will continue to travel across the cosmos, outliving the civilizations and technologies that study it. Its story is one of endurance and transformation, mirroring the broader narrative of the universe itself. As long as there are those who look to the stars with curiosity and determination, 3C273 will remain a source of inspiration. A journey without end. The journey of 3C273 is far from over. Each new generation of scientists will build upon the discoveries of the past, uncovering new layers of complexity and forging new connections between this extraordinary quasar and the larger universe. Its light, traveling across billions of years, is a reminder that the quest for knowledge is never-ending, a journey as vast and beautiful as the cosmos itself. In the eternal light of 3C273, we find not only a window to the universe but also a reflection of our own limitless potential. The infinite lessons of 3C273. The story of 3C273 is not just about the discovery of a quasar, it is a profound narrative that encapsulates humanity's relationship with the cosmos. As we continue to study this remarkable object, it teaches us lessons about the universe's complexity, the power of scientific discovery, and our capacity for exploration. Unraveling cosmic mysteries. Quasars and galaxy evolution. The discovery of 3C273 revealed that quasars are not isolated phenomena but rather integral components of galaxy evolution. During their quasar phase, galaxies undergo significant transformations, driven by the activity of their central supermassive black holes. By studying 3C273, astronomers have learned that quasar activity often coincides with periods of intense star formation and galaxy mergers. These events feed the supermassive black hole with vast amounts of gas and dust, triggering the release of enormous energy. This energy, in turn, influences the surrounding galaxy by heating gas, suppressing star formation, or even expelling material into intergalactic space. This feedback mechanism has profound implications for our understanding of galaxy evolution. Quasars like 3C273 demonstrate how the smallest scales, those near a black hole, can shape the largest structures in the universe. Quasars and supermassive black holes. The study of 3C273 has also advanced our understanding of supermassive black holes, their growth, and their role in shaping the universe. These enigmatic objects, millions to billions of times the mass of the Sun, are now recognized as the engines driving quasar activity. Through detailed observations of 3C273's accretion disk and jets, scientists have gained insights into how black holes consume matter and convert it into energy. This process, known as accretion, is one of the most efficient ways of generating energy in the universe, far surpassing nuclear fusion. The study of 3C273 has also provided clues about the formation of supermassive black holes. One possibility is that these objects grew rapidly in the early universe through the mergers of smaller black holes and the accretion of surrounding matter. Observing quasars like 3C273 at different stages of their evolution helps refine these models and answer fundamental questions about the origins of these cosmic giants. 3C273 as a universal benchmark. As one of the brightest and most accessible quasars, 3C273 serves as a universal benchmark for studying high-energy astrophysics, cosmology, and galaxy dynamics. Its well-documented history and extensive data make it a reference point for testing new theories and technologies. Testing relativity and physics at extreme scales. The extreme environments near 3C273's black hole offer natural laboratories for testing the laws of physics under conditions that cannot be replicated on Earth. Observations of the quasar's jets, for instance, provide opportunities to study relativistic effects, such as time dilation, beaming, and energy transfer in high-velocity systems. These studies not only validate Einstein's theory of general relativity but also push the boundaries of our understanding of physics. They help identify where current theories may break down, offering clues about the need for new frameworks that unify general relativity with quantum mechanics. Cultural resonance of 3C273. Beyond its scientific importance, 3C273 has become a cultural icon, symbolizing humanity's quest for knowledge and our connection to the cosmos. Its light, which began its journey billions of years ago, serves as a metaphor for the enduring impact of discovery and the infinite potential of human creativity. Inspiring art and literature. The beauty and mystery of 3C273 have inspired artists, writers, and philosophers to explore themes of time, light, and the interconnectedness of the universe. Its story has been depicted in literature, documentaries, and visual art, offering new ways of understanding the cosmos and humanity's place within it. A symbol of exploration. 3C273 represents the spirit of exploration that drives humanity to look beyond immediate horizons. Its discovery reminds us that even the faintest signals can lead to profound revelations and that the act of questioning and observing is fundamental to progress. Future Frontiers in 3C273 Research. As technology advances and our understanding of the universe deepens, the study of 3C273 will continue to evolve. New instruments, missions, and methodologies promise to unlock even more secrets about this remarkable quasar and the broader universe. Advanced computational models. The increasing power of computational modeling is allowing scientists to simulate the conditions around 3C273 with remarkable accuracy. These models combine data from multiple wavelengths, radio, optical, X-ray, and gamma-ray, to recreate the dynamics of its accretion disk, jets, and surrounding environment. These simulations help answer questions about how matter behaves under extreme gravity and magnetism, shedding light on the processes that drive quasar activity. They also enable predictions about how 3C273 might evolve over millions of years, offering a glimpse into its future. Global collaborations and observatories. As astronomy becomes an increasingly collaborative field, global networks of observatories are working together to study objects like 3C273. Projects such as the Event Horizon Telescope and the Very Long Baseline Interferometry (VLBI) array bring together telescopes from around the world to create Earth-sized instruments capable of resolving the smallest details of distant quasars. These collaborations are not limited to ground-based observatories. Space-based missions, such as the James Webb Space Telescope, JWST, the European Space Agency's Athena X-ray Observatory, and future gamma-ray observatories, will complement ground-based efforts, providing a comprehensive view of 3C273 across the electromagnetic spectrum. A legacy without end. As humanity's understanding of the universe continues to expand, 3C273 remains a cornerstone of discovery and inspiration. Its light, which began its journey billions of years ago, connects us to the ancient universe while pointing toward a future filled with possibilities. A bridge across time. The photons emitted by 3C273's accretion disks serve as a bridge across time and space, linking the distant past to the present. As long as we study and reflect upon this extraordinary object, its light will continue to guide us, offering insights into the nature of the cosmos and our own place within it. A guide for the future. As we look toward interstellar exploration and the discovery of new worlds, 3C273 will remain a constant presence, a navigational marker, and a symbol of the infinite. Its brilliance will remind us of the universe's vastness, beauty, and mystery, encouraging us to embrace the unknown and continue our journey into the stars. Conclusion: the endless light of 3C273. The story of 3C273 is far more than the discovery of a quasar. It is a celebration of human curiosity, resilience, and ingenuity. Its light, traveling across billions of years, carries with it the lessons of the cosmos, offering a glimpse into the universe's past, present, and future. As we continue to study this extraordinary object, we are reminded that the universe is not just a collection of stars and galaxies but a dynamic, interconnected system filled with wonders waiting to be uncovered. The journey of 3C273 is a journey shared by all of humanity, a journey of discovery, imagination, and boundless possibility. In the eternal brilliance of 3C273, we find not only the story of a quasar but the story of ourselves, our universe, and our endless quest to understand the infinite. The ever-expanding legacy of 3C273. The story of 3C273 is a continuous unfolding narrative, reflecting the interconnectedness of science, technology, and the human spirit. As we delve deeper into the mysteries of this extraordinary quasar, its light illuminates paths to new discoveries and inspires a broader understanding of the cosmos and our place within it. The intersection of science and imagination. 3C273 is not just a scientific marvel, it is also a symbol of humanity's capacity for imagination and exploration. The quasar's journey from obscurity to prominence in scientific literature mirrors humanity's own journey of discovery, an ongoing quest to uncover the unknown. A spark for future innovations. The technologies developed to study 3C273 have spurred innovation across multiple fields, from advanced imaging techniques to computational astrophysics. These tools, initially designed to observe distant quasars, now have applications in diverse areas such as medical imaging, remote sensing, and artificial intelligence. For example, algorithms developed for analyzing the variability of quasars are now used in Earth-based applications, including climate modeling and natural disaster prediction. The ability to process and interpret vast datasets, honed through studies of 3C273, has become a cornerstone of modern scientific inquiry across disciplines. Deepening the study of black hole physics. At the heart of 3C273 lies one of the universe's most enigmatic phenomena, a supermassive black hole. The study of 3C273 continues to provide unprecedented insights into the nature of black holes, their accretion disks, and the high-energy processes that define their environments. Understanding black hole spin. One of the current frontiers in black hole research is the measurement of spin, a fundamental property that influences how a black hole interacts with its surroundings. The spin of 3C273's black hole affects the dynamics of its accretion disk, the energy of its jets, and the overall luminosity of the quasar. By analyzing the X-ray emissions from the inner edge of 3C273's accretion disk, astronomers aim to constrain the black hole's spin, providing insights into its formation history. High-spin black holes suggest rapid growth through accretion, while lower spin rates point to growth dominated by mergers. Quasars and the search for cosmic answers. Quasars like 3C273 are more than isolated objects, they are keys to unlocking some of the most profound questions in cosmology. Their light, traveling across billions of light-years, carries information about the universe's origins, structure, and ultimate fate. Exploring cosmic dawn. 3C273 provides a glimpse into an era when the universe was younger and more active. By comparing it to even more distant quasars, astronomers can piece together a timeline of cosmic history, from the first light of the reionization era to the large-scale structure we see today. Studying quasars helps address questions such as: how did the first galaxies and supermassive black holes form? What role did quasars play in shaping their host galaxies and surrounding environments? How do the processes observed in quasars like 3C273 inform our understanding of galaxy evolution? Quasars and the fate of the universe. The study of quasars also sheds light on the universe's long-term trajectory. Observations of 3C273 and similar objects contribute to our understanding of dark energy, the mysterious force driving the acceleration of cosmic expansion. By mapping the distribution and redshift of quasars, astronomers refine models of dark energy's behavior over time, providing clues about whether the universe will expand forever, slow to a halt, or collapse in a big crunch. Cultural and humanistic reflections. While the scientific significance of 3C273 is immense, its impact on culture and philosophy is equally profound. The quasar's light, which has traveled across billions of years, challenges us to think about time, existence, and our connection to the cosmos in new ways. A bridge between science and art. The awe-inspiring nature of 3C273 has inspired artists and writers to explore themes of light, time, and interconnectedness. It symbolizes the fusion of art and science, as both disciplines seek to make sense of the universe in their own ways. From poetry that captures the quasar's brilliance to visual art that reimagines its jets and accretion disk, 3C273 serves as a muse for creative expression. Its story reminds us that science is not just a pursuit of facts but also a source of wonder and inspiration. The philosophy of scale. The vast distances and timescales associated with 3C273 force us to confront the limits of human perception. Its light, which began its journey billions of years ago, connects us to a universe that existed long before humans walked the earth. This perspective emphasizes the continuity of existence and the interconnectedness of all things. At the same time, the discovery of 3C273 highlights humanity's ability to transcend those limits through curiosity and innovation. By observing and understanding a quasar so distant and powerful, we affirm our capacity to explore and comprehend even the most remote corners of the universe. The infinite potential of 3C273. The study of 3C273 is far from complete. As technology advances and our questions become more sophisticated, this quasar will continue to serve as a guide and a challenge, inviting us to push the boundaries of knowledge. A model for future discoveries. 3C273's well-documented history and extensive data make it an ideal model for studying other quasars and high-energy phenomena. Future telescopes and instruments will allow scientists to compare 3C273 with newly discovered quasars, identifying patterns and anomalies that deepen our understanding of these extraordinary objects. A guide for cosmic navigation. As humanity moves toward interstellar exploration, objects like 3C273 will play a practical role as navigational beacons. Their brightness and stability make them ideal reference points for spacecraft venturing beyond the solar system, ensuring accurate navigation in the vastness of space. A timeless symbol of exploration. The journey of 3C273 is a reflection of humanity's own journey, a story of discovery, resilience, and infinite curiosity. Its light, which has traveled across eons to reach us, serves as a reminder that the universe is vast, beautiful, and filled with mysteries waiting to be uncovered. A legacy of inspiration. As scientists, artists, and dreamers continue to explore the cosmos, 3C273 will remain a symbol of what is possible when we look beyond ourselves. Its brilliance, both literal and metaphorical, challenges us to dream big and think boldly. A journey without end. The light of 3C273 will continue to shine, guiding humanity through the challenges and triumphs of exploration. Its story is not just about a quasar, it is about the limitless potential of science, imagination, and the enduring quest to understand the universe. In the eternal light of 3C273, we see not just a quasar but the infinite possibilities of discovery and the unyielding brilliance of the human spirit. The expanding role of 3C273 in scientific exploration. As we continue to push the boundaries of astronomy and cosmology, 3C273 stands as a foundational pillar, offering insights into phenomena that are central to understanding the universe. Its multifaceted nature ensures that it will remain a focus of research across numerous scientific disciplines. Quasars and the evolution of the early universe. Quasars like 3C273 serve as time capsules, preserving the conditions of the early universe. The light from 3C273 has traveled over 2 billion years to reach us, providing a snapshot of a period when galaxies and black holes were actively evolving. Probing the epoch of reionization. The epoch of reionization marks the time when the first stars and galaxies began to form, ionizing the neutral hydrogen that filled the universe. 3C273 offers indirect evidence of this era by illuminating the intergalactic medium, IGM, it passes through. By studying its spectrum, astronomers can map the ionization history of the universe and identify the processes that led to the reionization of cosmic gas. This research addresses critical questions about the formation of the first structures in the universe and how they influenced the large-scale organization of matter we observe today. The birth and growth of supermassive black holes. One of the enduring mysteries in astrophysics is how supermassive black holes, like the one powering 3C273, formed so quickly after the Big Bang. Theories suggest that early black holes may have originated from the collapse of massive stars or the direct collapse of gas clouds. By studying the properties of 3C273 and comparing it to other quasars, scientists gain insights into the mechanisms that allowed these black holes to grow rapidly, whether through accretion of gas, mergers with other black holes, or a combination of processes. Understanding this growth helps us piece together the early stages of galaxy evolution and the role of black holes in shaping the cosmos. Unveiling the complexity of quasar jets. The relativistic jets emitted by 3C273 are among its most striking features. These high-energy streams of particles, traveling at nearly the speed of light, extend for hundreds of thousands of light-years and are visible across multiple wavelengths. The physics of relativistic jets. Jets like those of 3C273 are believed to arise from interactions between the accretion disk and the magnetic fields surrounding the black hole. The particles in the jets are accelerated to near-light speeds, emitting radiation across the electromagnetic spectrum. Studying these jets provides insights into the mechanisms of particle acceleration, the role of magnetic fields in shaping jet dynamics, the impact of jets on the surrounding intergalactic medium. Future high-resolution imaging, such as that enabled by the Event Horizon Telescope, EHT, and upcoming missions, will allow scientists to resolve the fine structures within these jets, providing a more detailed understanding of their origin and behavior. Jets as cosmic engines. The energy and material carried by quasar jets can influence their host galaxies and surrounding environments. In the case of 3C273, its jets are thought to heat and expel gas, regulating star formation and contributing to the chemical enrichment of the intergalactic medium. These interactions are critical for understanding the feedback mechanisms that govern galaxy evolution and the broader ecosystem of the universe. Quasars and the search for universal constants. Quasars like 3C273 are also valuable tools for probing fundamental constants of nature, such as the speed of light, the gravitational constant, and the fine structure constant. By analyzing the spectra of distant quasars, scientists can test whether these constants have remained stable over cosmic time. Probing the stability of physical laws. If variations in universal constants were detected, it would have profound implications for physics, suggesting that the laws governing the universe might evolve over time. 3C273, with its bright and well-studied spectrum, provides a reliable data source for conducting these tests. This research intersects with theories of quantum gravity, string theory, and other cutting-edge areas of physics, offering potential insights into the fundamental nature of reality. The role of 3C273 in big data astronomy. The vast amount of data generated by modern observatories has transformed astronomy into a field increasingly driven by big data. Quasars like 3C273 are central to this revolution, serving as key targets for large-scale surveys and computational analysis. Harnessing artificial intelligence. Artificial intelligence, AI, and machine learning algorithms are now used to analyze the variability, spectra, and light curves of 3C273 and other quasars. These tools can identify subtle patterns and correlations, uncovering relationships that might otherwise go unnoticed. For example, AI-driven analysis of 3C273's variability has provided new insights into the dynamics of its accretion disk and the physical processes driving its luminosity. These methods are becoming increasingly important as telescopes generate petabytes of data annually. Citizen science and public engagement. Projects like Zooniverse have invited the public to contribute to the analysis of astronomical data, including observations of quasars. 3C273 has become a popular target for citizen scientists, who help identify patterns and anomalies in its behavior. This collaboration not only advances scientific research but also fosters a sense of connection between the public and the cosmos. 3C273 as a cosmic timekeeper. The regularity of 3C273's variability and its well-documented history make it a valuable tool for calibrating instruments and testing timekeeping in astrophysical observations. Its consistent brightness across billions of years allows scientists to compare data from different telescopes and epochs, ensuring accuracy and consistency. A standard candle for quasars. While supernovae are commonly used as standard candles for measuring cosmic distances, quasars like 3C273 are emerging as complementary tools. Their extreme brightness and detectability across vast distances make them ideal for studying the far reaches of the universe. Future research aims to refine quasars as standard candles by identifying relationships between their luminosity and other observable properties. 3C273 is at the forefront of this effort, serving as a model for understanding quasar variability and its connection to intrinsic luminosity. A symbol of endless exploration. As we look to the future, 3C273 remains a symbol of humanity's unyielding drive to explore, understand, and innovate. Its light, traveling across billions of light-years, connects us to the distant past while guiding us toward the boundless possibilities of the future. An eternal beacon. The light of 3C273 will continue to shine for billions of years, outlasting the civilizations and technologies that study it. Its enduring brilliance reminds us that the universe is far larger and older than we can fully comprehend, yet within our reach to explore and understand. Inspiring generations to come. The story of 3C273 is one of curiosity, perseverance, and discovery. It challenges us to look beyond our immediate surroundings and embrace the vastness of the cosmos. For scientists, artists, educators, and dreamers, 3C273 is more than a quasar, it is a reminder